Okay, good start. Okay. Morning, everyone. Thank you very much for coming along. My name's Noel. The idea of this talk is to give a very, very swift overview into Scalaz. Just out of interest, do people here use Scalaz? Many? Yeah. Okay. Does anybody not use Scalaz or doesn't know what it is? Has anyone seen Scalaz and maybe is a bit scared of it? It's weird language and symbols and things like that. Well, the idea of this talk really is to hopefully debunk a few of the myths and weird symbols, and maybe by the end of it you'll want to include Scalaz and see some reasons as to why that's a good thing. So I've given it the title, How I Learned to Stop Worrying and Love Monads. It's a little bit about me. Hello, my name's Noel. I work in London for a company called ITV, with the largest commercial broadcaster in the UK. And I work on our Common Platform Services team, and we are re-architecting a lot of our online offerings, so online catch-up across multiple platforms and devices, and trying to make that as coherent as possible and as easy to onboard new devices whenever possible. In a previous life, I wrote a book on Java programming interviews, so maybe if you fancy a challenge after the conference, you could go back to Java. Okay, so a little bit about what we're going to talk about today. So just some things that as soon as you import Scalaz in your project, what you get for free. A new type. I'm going to spend a little bit of time talking about exactly what type classes are, and then the type classes that Scala provides and some instances for them. And then towards the end we'll talk about everyone's favourite topic. Okay. So to import Scalaz, really, really simple. So make this a bit bigger. Is that okay at the back? Yeah, okay. Well, the slides will be online later, and I'll zoom in if there's any questions or anything. So it's a one-line SVT import. If you can't read it, look on the GitHub project. And then generally you need a pair of imports. The first import with a lowercase is a root import, and that will give you all the types that Scala provides. And the second one, Scalaz, is the enhancements that you get for lots of different types, and we'll look at a few of those right now.
Is it possible to zoom in?
I'll zoom in when necessary. Unfortunately, the slides are at a slightly different resolution to what I did them at, but we can definitely.
Even from the first row, it's not easy to see all what is written, and for people who are
How's
it's
that?
better
Yeah?
now.
I might have to zoom in and out a little bit. Yeah. we can discuss this as we go along. Okay. So straight out of the box, as soon as we've got our imports, we get lots of extra methods. I think the correct term is called enhance my type. So for instance, on booleans, we get a method called .option, which takes one parameter, and if we call .option on a boolean, then the parameterized value is returned inside an option if it's true, or none if it's not. And in my opinion, this is probably a little bit easier to read than say if boolean, then some of something, otherwise none. It just seems to read a little bit nicer for me. For strings, we get methods like parse primitives. So let me zoom in a little bit on this. So we can call parseInt on a string, and if that does contain a string, then what we get returned is a validation object, which, if you're not too familiar with that, is it's a little bit like an either in Scala. So the kind of left-hand type or the failed type, it would be the exception on why it couldn't parse that value into the given type, and the success type, or maybe the right, is the actual type. So here 6.parseInt, we get a 6 inside of success, and that's a real integer. We can add and subtract and do all the fun stuff we do with integers. Similar for parse boolean, and there's plenty of these for all the primitive types. For lists, there's plenty of methods on lists. Just a couple I kind of picked out here. All pairs. So we go through each value inside the list and create permutations of all pairs there. .power set, if you ever needed that, maybe in your next job interview. And we get all the different subsets of given elements inside a list. Now these are not just for specific types. We do get some for all types. For instance, .sum. So here we can call .sum on any single type. And this gives us that inside an option. So if we have a method that needs an optional type and we've got a concrete one, we can just put .sum at the end. Of course, we can just call the sum constructor. There is a slight difference here, but if you can see here is that this first one, res6, is returning, it has a type of option of string, and this is a sum of string because we've used the sum constructor, and Scala isn't smart enough to work out that we actually want an option. Generally, this isn't an issue, but there are some times where you may get a little bit confused. You don't need to worry about what this operator does. We'll come on to that a little bit later, but if we do things like this, Scala just gets a little bit confused, but it works fine if we call it just .sum. We can do this as well for any type, so not just provided ones, but if we create our own type, then we can use .sum on that. And this is the same for any of the operations that work on any type. And there's plenty of these. Have a look through the source code. You pull out the autocomplete drop-down inside your favorite IDE, you'll find there's plenty there, and they really are quite useful. So another thing that Scala gives, and Brendan, I don't know if people saw Brendan's talk yesterday, he mentioned this as well, is that there's a better either. So Scala has an either A or B, and I expect most people are probably familiar with that. And Scala Z provides one as well, which has this slightly odd syntax, if you've not seen this before, and this is called a disjunction. And often when I describe this to people who are slightly new to Scala, is that people don't often know that if you have a type constructor with 2 parameters, you can actually use infix notation, and things become a little bit clearer, I think. So you would generally read this as A or B. That symbol is called disjunction. People call it either, disjunction. There we go. And you can use this, in my opinion, this probably makes things a little bit easier to read. So if you have methods, say, returning an exception or an HTTP response, you've got a good idea that, something may go wrong, and if it does, at least you can get hold of the exception that occurred. You can have this is dead? Sorry. I'm sorry about the size of the slides. It's a slightly different resolution to what I prepared it in, but they will be online. And do shout out if there's something you want to clarify.
Is that statement of the HTTP response?
Yes. So the part on the left is the I suppose you'd call it the lesser of the 2 types. There's nothing here that says this is to be used for errors, but we'll look at the next slide in a minute, and generally the right-hand type is a little bit more dominant. That'll come clear in a sec. In fact, right now. So here, this probably looks quite familiar to anyone who's used Scala's either. So we call the right, and then if we want to operate on that right, we have to go .right.map. If we wanted to work on the left-hand type, we'd call .left.map or flat map or whatever. But the thing with the Scala disjunction is a phrase that's often uses it biases to the right. So there's no need to project onto the right or the left and then call .map. Is that we can just call .map itself. And again, we've got a little bit more weird symbols here, but basically this is the disjunction. We're saying we're on the right-hand side of it here. and then we call .map, and this just works the same way. So we've got a function here to do whatever we need. So the nice thing here is that generally when you're returning an either, it's not like both types have the same priority. You know, one generally is more important than the other. So like we'd normally have an error or the value we wanted, and Scalaz's either kind of reflects that. There's methods here for swapping them around. There's a left map method. So you can work with both types. But generally, a nice way to think about this is probably like an option. So we just have an option, and we call .map, and it just works as you would expect. So one thing I've often found with this either is when I've introduced this to colleagues, is that they say things like, can we not give this a better name? I'm really uncomfortable with the kind of // approach. And if you want to introduce it either, maybe these are a couple of arguments that you can kind of back to colleagues and to be using this. Is that the first thing they say, well, it's just a mathematical symbol, you know, it's or, and it's just a mathematical symbol, much like plus. I found probably about 60% of people I say that to, then it kind of clicks straight away, and they're like, oh, okay, it's just one I didn't use at all. And if people still don't want to use it, you can say, well, let's use it for a week. We'll just get used to it, have a bit of a play around with it. And if we're still not happy, maybe we'll discuss it after that. And honestly, I've never had that discussion or needed to. But then my next port of call will always be, well, we can always hide this, and then we get all the benefits of using the either, and we can treat it just like any other type, and we just hide it away. This might be a nice way to introduce it, and then you can just think of this like an option where we've also captured what happens when things go wrong. Okay? So probably the strongest motivation for using Scalaz is type classes. And this can be maybe a slightly, this is probably a new thing to people who've come from an imperative, you know, like a Java or C# background. So I thought it would be interesting here just to try and define a type class with a simple example. And I've just ripped this off completely from the original paper that Martin Adersky wrote on introducing type classes and implicits in Scala. So let's say we had a trait for defining order here. Now, we've got one method here, compare. It takes two values of the same type and returns a Boolean. This might not be the best API in the world, but you know, we can work with this for now. And what we'll say here is that if A comes before B, then we'll return true. And then whatever the T's are, or whatever we implement this for, we can then get a sense of order. So once we've got this trait, we can create an instance of this trait for a specific type. In this case, we've got a type for integers. So now if we're presented with a pair of integers, we know which one comes first. Hopefully this isn't too out of the ordinary for people. And now we can use this. So say we have a sort method, which is parameterized on T. It takes a list of that type T, and we've got a curry method, a curry parameter list. So we've got a second parameter list of the ordering. I think this makes sense, doesn't it? We can then implement using this ordering to create a sorted list. And if we wanted a different ordering, maybe we wanted reverse, we can change this to be greater than or equal to, or something like that. And this works, so we can sort using this. But it's a little bit unwieldy, really, because we're kind of carrying this order around. We know we need it, but it just feels a little bit unwieldy, probably not too helpful. So what we can do is we can make this ordering implicit. It's the standard Scala keyword, and then this makes this available to the compiler whenever we find an implicit parameter. So the rest of the implementation will be exactly as it was before, but now we've got this implicit parameter list of ordering. And if we ever want to use this sort, as long as there is an ord of t in scope for the list of t that we want to sort over, this will just work. And I think that tends to be a little bit kind of more understandable. And if there's no implicit in scope at all, then we get a compiler error. This isn't a runtime error, it doesn't do something randomly, it doesn't do nothing at all. It actually won't even compile. So this is great. You know, the compiler's helping you here, it's flagging up that it doesn't know exactly what to do, and you're not going to be sat at 3 AM looking at production logs, wondering why your implicit isn't working. Okay? That make sense? If this is a little bit confusing or you're not quite following this, you've probably seen this before already. This exists in Java. We have a comparator interface, pretty much the same thing. And this gets used all over the place as well. It's not implicit, you do have to carry this around, it does give you that power. It's all over the place, collections.sort, arrays.sort. I think it's used a lot in the tree map functions, and so on. So Scalaz gives plenty of type classes. So we've just looked at one for ordering here, but there's others as well. So we've got equality. These are ones I just thought of off the top of my head, the ones I use. Functor, monad, applicative, there's plenty of these. So the terminology and language might be a bit strange, but I suppose the point of this talk really is to show that it's not that scary, really. So let's have a look at one of these type classes, equality. So what this gives is this gives a new operator here, this triple equals. And it works in pretty much the same way as double equals. So something on the left, something on the right, compare them. If they're equal, it's true. If they're not equal, it's false. However, if you try to compare two things of different types, that's never ever going to return true. But it's even better, is that the compiler can step in for us. And so we're trying to compare two things of different types. And this is great. So you could imagine maybe a scenario here, you might be doing a little bit of refactoring. You've got a certain type, you change it to be optional. Later on in your code, you're trying to compare it with something else. All of a sudden, you're comparing option of A with A. But now the compiler's going to step in and say, look, this isn't going to work. This is never going to work. So you need to change that.
Usually I get compiler warnings just for ordinary equals. Also.
Yeah, but this actually stops it from working, because a warning is great, but it's never ever going to return true. You know, so the thing here is that we're saying that there is no point comparing a string with an integer or something else, because they're not the same type. They are never going to be equal. And yeah, you're absolutely right. Those warnings are great. And I think you can probably even change IDE settings to flag up a compiler error rather than a warning, but this is built into the language. So if we have our own type, it might be nice if we want to use this triple equals with our own types. So say we've got some class here. I've purposefully not made this a case class, but we've got a class and perhaps we don't have source code, or we can't change it, or this is being auto-generated from somewhere else. All we have to do is provide an implementation of the equal type class for money. And there's one method to implement equal, which takes two money parameters and then returns a Boolean. And you can see here that actually what I've done is use the triple equals in both cases, because Scalaz provides triple equals for both string and int, amongst other types, out of the box. So we know here that at least we're being type safe in our comparison of the types within our own types. And now we can just compare things. I mean, obviously this will return false, but at least we know that we're comparing apples with apples. And then if we do have a case class, we can do this slightly easier, because we can use the equality method from that class. Or in fact, this works not just for case classes, but for any class where we just want to use what would generally be Java's equals. We know that we can be safe with that. We can use this equal A, and that will just do that for us. Okay, another type class is a functor. It's got a funny name, but it's really, really quite simple. It's simply something that can be mapped. And I'm sure you can think of plenty of these. So we can map lists, we can map options, we can map futures. So what we need to do here, what we want to have a look at here is can we like abstract this? Is there a pattern here? Can we make use of the fact that all these things map? Maybe there might be a time where we want a very, very generic function where we might want to map over a list in one instance or an option in another. And thankfully, Scalaz gives us that. So I've I kind of thought this up on the spot, really. But just give you a second or two to have a look at what this does. Okay, so what we've got here is we've got an addInt, and all I want to do is add a number to a functor of a number, so like a list of integers or an optional integer or a future of integer or whatever. And we've got we've got a type parameter here. I don't know if this is news to anyone or if this is a bit unusual. Often when I've shown this to people, they don't often know what this part means here. Generally, this means that f is a type constructor, and then it needs another type in order to become a real type. Like you can't have a list of, you can't just have a list in Scala. It has to be a list of integers or strings or money or whatever. So what we're saying here is that we need a type constructor for this. So we've got our parameters here, an int, and then what we want to add to, and then that's our type constructed for int. And then Scalaz provides us with a functor. And as long as we have a functor, then this method will compile. And what the functor class gives us is this map method. And generally what that does on its implementations is call the underlying map method. So for lists, that will call .map, and then it will, whatever you're mapping over will apply to all values in the list, and so on. So here we've now got this generic function which allows us to add a number to something containing numbers, if that makes sense. So we can add 6 to an optional integer, we can add 2 to a list of integers, we can even add 100 to something that hasn't even happened yet. Is that all okay? Okay. I won't spend long on this, but here's a small, kind of fictitious scenario, I suppose. So say we've got a function here which takes 3 integers and adds them together. And then also we've got a map which contains strings to numbers. And say, for instance, we wanted to pull values out of this map and add them together. However, there's a slight problem here, especially if we're trying to be type safe, is that when we get numbers out of the map, we don't actually get the numbers, we get optional values of the numbers. So somehow we need to get into that option itself. And we're all good programmers, and we don't want to call .get because that might blow up if we call it for a wrong value. So Scalaz provides us with what's called Applicative, and we've got a little bit more funny syntax here. And there's lots of discussions as to what this is called. But this is an applicative builder. And so we take 3 optional values here. So it's an option of A, option of B, option of C. In this case, they're all optional integers. And then we have a curried function which is a function for A, B, and C to some value. And then it will give us the optional result. So in this case, it's going to take option of 4, option of 5, option of 6. And then we've got a function here which, when we give them with sums, it's going to add them together and return the result in a sum. And the nice thing with this is it respects options. So if we do call this with a value that's not in our map, we get a none back, then we get none, because we can't do this. So one way to think about this is it's like the map, but it's for an arbitrary number of arguments. So as long as we've got the optional types, and then we've got a function that works on those underlying types, then we can do things like this. And this is often called lifting. So we're lifting this sum function into options. Of course, this doesn't just work for applicative. This doesn't just work for options. This works for anything which has an applicative type class. So, you know, out of the box, this will be working with lists and futures with the right import and so on. Okay, I think this is at least the 4th time I've seen monoids defined here this week, but I'm going to have another go. So, a new type class, monoid. So, monoid is actually built up from 2 things. Is that we have a semigroup and a monoid itself. So, a semigroup has, well, in ScalaZ's implementation, it has 2 methods. So, we've got append here. So, we've got 2 values of the same type, f, and then we get a value of that same type back. We'll have a look in a minute how that works. And then we've got another funny symbol here, so we've got pipe plus pipe. But then the great thing is we don't have to do anything with that because that's just alias to append. And then a monoid is a semigroup with this extra function here. So this function defined as 0, takes no parameters, and just returns an instance of the type f. So what we've got here is an associative binary operation and an identity element. So a binary operation, that's just a function which takes 2 parameters. And then for it to be associative, all we have to make sure is that this rule is the same as this rule. So that's if we add A to B plus C, we get the same as adding B and C together and then adding A to the end of that. And you can probably think of plenty of examples of this. Addition, multiplication, string concatenation, list concatenation. You know, you can probably think of more than I can right now. And then we also have this identity element. And the way to think of the identity element is that if we include the identity element in our binary operation, it has no effect. So for instance, for addition, we add 0 to something, it has no effect. For multiplication, we multiply it by 1, it has no effect. String concatenation, empty string, list concatenation, and so on. Any ideas what an identity operation would be for this? Integer.min, if you can't read it.
Maxim.
Yeah, maxim. If we compare 2 integers looking for the minimum, and one of them is the maximum, then regardless, we're getting the other value, even if that's maximum as well. I won't give you the answer to this, but what about booleans? Have a think about that. The answer's in the source code. So, with a monoid, we get another enhanced method that we can use on things like lists, called FoldMap. So what the FoldMap takes is a function, and the parameter is the type of the element in the list, and we need to return a monoid value. So here we're just using identity because that holds. So we pass in an integer parameter, and then monoid, integer is a monoid. And by default in ScalaZ that uses addition rather than multiplication. So this has the effect of adding these elements in the list. This is much like using a fold left or a fold right, where our initial value is the identity element in that list. So we've got the identity element, 0, plus 10, plus 9, plus 8, gives 27. That's a lot nicer to read, I think, than the fold left or the fold right, especially when you use that slash colon or whatever way around it is, I can never remember. And of course, you know, you can probably think of plenty of things that you could use this for. So here, our function needs to take a string and return a monoid. And in this case, we're returning a list. So our function just computes the length of each string, puts that in a list. And then we concatenate these, again, starting with the empty list, but for our concatenation, and we just get a list of all the lengths of strings. Again, there was this append method which I pointed out a couple of slides ago. And hopefully you understand this by now. So that's using this binary operation. So here we've got the plus. So for integers, like I said, by default we have plus. So this makes 6. And the nice thing is, a nice property is if we if type A has a monoid, then the option of type A also has a monoid as well, which means that any appending or operations we do works inside the option. So we can do really, really cool things like this. So if we've got a pair of optional strings, maybe some of them are none values, then we can still use this append here. And the nice thing is that the none is when using the none with binary operation, that's just the identity element. So it has no effect at all. So if you were trying to, I don't know, sum up a list of options, some of them might be none, but you don't care, this might be of use. So like I said, if an option, if A is a monoid, then an option of A is a monoid as well. And here's another example, but not using options. So let's take a look at that. And so we've got a map from integers to lists, some kind of key maybe. We've got two of these maps. Has anyone got any idea what M1 append M2 will return?
Concatenate the list inside the map.
Yeah, it basically kind of smashes the two lists together. So the nice thing here is that if the value type of a map is a monoid, then the map itself is a monoid. So that's quite nice, isn't it? Because you can imagine probably sometimes you use that. You're iterating over a list. You're iterating over a map and say, if the key is in the map, they get the list. Else create a new list and add the element to it. That all just goes away, really, doesn't it? Here's a similar example. Any idea what this will return? Yeah, so by default integers use addition, so we're just going to add these numbers together. So A maps to 2, there's only one C in there, there's only one B. That's pretty cool. So you might be able to see that there's some pretty funky things you can do with this, straight out of the box. So back to using this FoldMap, like I said, all we need to do is return a monoid from our FoldMap function. If we've got a list of elements and we want to group these up and count how many of each there are, that's quite nice. In my opinion, I really like FoldMap. I think that's one of the most powerful things. And this is not just for lists as well. This is on FoldMap is on a lot of types. So for instance, if you had options and you wanted, say you had an optional integer and you went got get or else 0, you can just call FoldMap. And then if it is a none, you'll get the identity value back. Similar for strings, if you have an optional string that you want to just pull it out and have an empty string, if it's none, FoldMap with ID. All good? Okay. Well, that's everyone's favourite topic. I'm just going to zoom out a second. Okay, so I'd just like to say a little bit about my experience with monads. They're not that strange. They're not that confusing. If they had a different name, then I think there would be less talk about them. They're not as confusing as the internet seems to think. There are plenty of silly stories about monads on the internet, burritos and astronauts and programmable semicolons and things like that. My advice is just use them, and then you'll understand them a lot quicker than following how someone else got to understand them. Another thing, personally, I think FOR, for comprehension, I think that name is really confusing to a newcomer. If you see the for, and you've seen the light with Java and you want to become a Scala developer, is that you're thinking, great, right, I can loop here, I can do some looping. Whereas actually that's not what happens at all. And again, I think when people start out with monads and they look at the list monad, it's quite tricky and quite funky the way it works, and it tends to be a little bit confusing. I tend to have had most success with people when they tend to start with maybe single element containers, maybe like a future or option, comparing futures and options and seeing the relationship between them and what you can do. And then maybe I'll just say a couple more positive things as well. if you have an API that returns a monad of something, then everything else just tends to fit together really nicely. And we'll have a look at exactly what that means over the next couple of slides. And then my absolute favorite thing is that if you abstract over monads themselves, like, it blows your mind. And we'll have a look at that as well. So when people ask me what is a monad, I'll throw my hat in the ring here and say what my definition is. Is that a monad encapsulates a specific pattern. It occurs so frequently in programming and functional programming generally that it is very, very useful. That's it. Perhaps it's a little bit abstract, so it might be worth having a look at a few examples here. So say, for instance, we've got a map. It's got maybe the keys in the map are integers. We want to pull out a couple of these integers and divide one by the other. So what generally happens here? As we've already seen, when we retrieve values from a map, we don't get that value back. We get the option of that value back because it might not be there. And then, of course, when we divide two numbers together, there's a possibility that we might try to divide by 0, and that's generally not a good thing. So let me zoom in a little bit here. So here, I think these two methods are okay. People seem to understand them. Is that you might get the option you might get the value from the map, and you might get a result when you divide two numbers. Another example here. Say we want to get some data from a web page. Maybe we'll do something with it and then write it to a database. So the first thing we're going to do here is make an HTTP call, which will eventually happen. And then we're going to store this in the database, and again, that takes time to work as well. So the thing here is we've spotted a bit of a pattern, is that, essentially this get method returns a B, generally. But there's some extra behavior in here. The persist method, it will complete once it's happened. So now we've got this extra behavior and we've spotted it. Is this useful? Can we kind of form some kind of abstraction over this? Well, Scalaz provides its own monad implementation. See, zoom in slightly more on this as well. So this is slightly condensed. This is not the full code, but basically we can split this into four methods, or four sections. Sorry. So we've got a couple of abstract methods here, point and bind, and then we've got flat map and this weird symbol, which are actually just alias to bind, so we don't need to worry about them. And then we've got map, and map is actually implemented in terms of bind and point. And that's the same map that we've seen before. So one thing that's really good here is that if something's a monad, it's a functor as well, and we just get that for free. So we can map on these just by providing point and bind methods. So what are these point and bind methods? So point, what's this say? It says given an A, this will give me an M of A. And what this generally means, so if we're thinking in terms of an option, if we call point with a value, we're going to get a sum of that value back. If we call it with a future, we're going to get a future of that value back, which has already completed. Generally, the rule with point is that it must return the default minimal context, I believe it's called, which basically means it's always going to be representative of the value of A. So this method, say, should never return a none. The future should always complete, and so on. And we've got this bind method as well. I don't think that's going to fit on the screen. Yep. Okay. So this is obviously a little bit more complicated here. We've got two type parameters for the start. And what does this say? Well, it says if I've got a monad of something, and I've got a function that takes a plain old A and gives me a monad of B, then this gives me an M of B. Now maybe this doesn't seem particularly useful, but as soon as you notice this, you start seeing this pattern all over the place, A to M of B. I've shown a couple of examples here already.
Doesn't it do something like flat map here?
Yes, this is flat map, but generally it's called bind. And actually, if we go back to that slide here, flat map, it's just alias to bind. That's it. Hi.
Just to point one thing, when you use this abstraction, for me, you don't need to show me your implementation. You can guess how you will implement it.
Yes.
Just see this, say, signature. You can guess what you.
Yes.
You can't get an MB without applying what you say the F in some way to the FA.
Yeah.
I mean, it's clear.
Exactly.
I've
spoken with people before who've implemented it for some time, and you say something. Oh, how did you implement that? It's like, I can't remember. It's like I know it works. I know it fulfills this contract, so it just works. And then
powerful.
Yeah.
Using all these places.
Exactly.
You can go back to the example you wrote to add int.
Yeah.
At the first one, when you use a functor, if you abstract over int to use any a and extract the addition as an operation from a to a, you can guess exactly what you
Indeed. Yeah, and this is great because this means we're actually going to be more productive. We don't need to be worrying about the nuts and bolts of this. This just works, and then we can get on writing our really fun business code instead. Yeah. So here, if we have a function for a to m of b, you might find then there's a function from b to m of c, and c to m of d, and so on. And we can basically build up these chains. So here's another fictitious scenario. So maybe this would be some business logic. So you've got a function that, given a username, returns their user ID. Of course, you might not give a username that exists. And then we can maybe go from a user ID to a fully fledged user object. And then again, maybe this is some kind of funky ORM where we can go directly from a user object to someone's address. Maybe the address isn't necessarily associated with the user for this particular business. And we can just chain these together, and we can basically go and get a method that gets someone's address just given their username. And we can use a flat map once that bind is implemented. And then here, if any of these functions fail, and we return a null, then of course we're going to get a null, because what else can we do that would fail here? And maybe this isn't strong enough because we don't know why we failed, so we might use an either in this case, or the disjunction type, but yeah. And then of course, as I said, we've got this weird symbol here. People often pronounce this bind, maybe flat map. It does the same thing. And the thing here is the compiler is actually enforcing the types of this chain. So the get user ID returns an optional int. So the operation after this bind method must be an int to an option of something. In this case, that something is a user, which means get address must be a user to an option of something. And that's what the whole method returns. Hopefully this all kind of, you've probably seen things like this before. Hopefully this isn't too out of the blue. This is actually so powerful that it comes for free in Scala. Okay? So we got 4 comprehensions here. I'm slightly running out of time, so I'm going to skip along. But basically, this unravels to a flat map, and then the value here is the value inside the context of the flat map. And this actually is completely given for free with Scala. You don't need to implement a particular interface or anything like that. As long as map and flat map are defined, this works. Of course, if you want to use the Scala's Z monads, it has to implement the monad trait. And different monads give different behavior. So this is kind of an external to what happens. So we've got option, we've seen the ability to fail fast. Disjunction is the same, but it lets us talk about actually what failed. Future performs computations concurrently. And there's other ones as well. We've got this reader, which we're not going to get time to talk about today. Or ID, which actually does nothing at all. So maybe have a think if there's any use for that, whether that makes any sense at all. And this is just my last section here. So say we've got another little scenario here, so similar to before, but maybe we're working in the future instead. So given a user, this goes off to some database or some REST service and gives us a user address, maps the user into address. And this shouldn't really be of any surprise to anyone now. You know, I could have done this using .flatmap or that bind operation. That's beside it. So maybe here we can do a slight refactoring. And then what we could do is we could abstract out these functions. So here we can take an integer to a future of user, user to a future of address, and we can wire these in at a later point. And that makes testing a lot easier, because then we don't need to be going off to our mighty Oracle database to go and test this. And then maybe we can refactor this one step further, and that we will abstract over the monad itself. So by adding a type parameter here, which we've seen this pattern before, constrain it to the monad, we can say here that for an integer, return some monad of user and for user some monad of address. And then in our production code, we would use the functions we saw a minute ago to a future. And here, this code hasn't changed at all. And then what this does is, in our tests, we could use a different monad in order to test this code. So if we use this magical ID monad, it does nothing at all. The ID monad is actually just a alias in Scala, in ScalaZ. So it'd be ID of A is A. So we can just return the users like so. And then this makes writing our tests much nicer, because we don't even have to wait for a feature to complete, because there is no feature. And then this becomes a lot more powerful, because we can return any old monad as long as it conforms to these values. So say we had some kind of long-running calculation, return a future of integer, and we do this ourselves. We're not calling a framework which returns a future or anything like that. We do the work ourselves. So we could change this to actually, we can provide the monad type, and then we get the monad in our response. And then we can call this point method, which means in our production code, we'd be using futures, but then in our tests, where we might want to a little bit more control over the way we use it, we can just call ID, and then we don't need any of the awaits or polling or things like that. That's actually about all I had to say. Sorry, I slightly went over ever so slightly. But yeah, if anyone has any questions, I'll put these slides up on the internet, or feel free to come and have a chat to me, or hit me on Twitter. No? Was everyone either mind blown or bored? Well, thank you very much.